Welcome to this walkthrough of LeetCode problem number 2045, second minimum time to reach destination. In this session, we'll explore the problem requirements, break down the solution approach, and highlight key concepts to help you master this challenge. Let's dive in. The problem revolves around a directed graph that represents a transportation system. This graph consists of n nodes, numbered from 1 to n, where each node can have at most one outgoing edge. The graph is described by the edges array, where each entry, u, v, time, indicates a directed edge from node u to node v, and the traversal of this edge takes time seconds. The paths in this graph are unidirectional, meaning you can only travel in the direction specified by the edge. Your task is to calculate the second minimum time required to travel from node 1, which is the starting point, to node n, the destination. If a second minimum time cannot be determined, you'll return -1. The input parameters include the number of nodes n, the list of directed edges, and a traversal time. The output is a single integer that represents the second minimum time to reach the destination, or -1 if no valid second path exists. To better understand the problem, let's consider an example. Here, n is 5, and the edges array specifies the graph structure with edges like 1, 2, 2, which means there's a directed edge from node 1 to node 2 with a travel time of 2 seconds. The traversal time is given as 3. The output for this example is 6. The explanation is as follows. The shortest path from node 1 to node 5 is through the route 1-3-4-5, which has a total travel time of 6 seconds. A second valid path exists, 1-2-4-5, but its travel time is 8 seconds. Since we're interested in the second minimum travel time, the answer remains 6 seconds. Taking another example, let's say n is 6, and the edges array describes a slightly larger graph. Here, the traversal time is 5, and the output is 10. Here's why. The shortest path from node 1 to node 6 is the route 1-4-5-6, with a total travel time of 11 seconds. However, a second path exists, 1-2-3-6, with a travel time of 12 seconds. After adjusting for the traversal time, the second minimum travel time turns out to be 10 seconds. The task involves carefully considering all paths to ensure that the correct second minimum time is calculated. When solving this problem, it's important to note some constraints and edge cases. First, the graph can contain up to 1,000 nodes and 2,000 edges, which means the solution needs to be efficient to handle larger inputs. Additionally, there are no self-loops in the graph, meaning edges like u are not allowed. For edge cases, consider disconnected graphs where no paths exist between nodes 1 and n. In such cases, the output should be -1. Similarly, if there's only one valid path between the nodes, no second minimum time exists, so the output is also -1. Finally, when multiple paths have the same travel time, the solution must correctly distinguish between the shortest and second shortest paths. These considerations ensure that the solution is both correct and optimal for a wide range of scenarios. To solve problem number 2045, we need to find the second shortest time to travel from node 1 to node n in a weighted, directed graph. This problem is essentially a variation of the shortest path problem, but with the added complexity of tracking the second shortest time. One approach we might consider is the brute force method. The idea here is to explore all possible paths from node 1 to node n using either depth-first search or breadth-first search. As we traverse the graph, we would calculate the time taken for each path, keeping track of the two smallest times that allow us to reach the destination. This would let us return the second smallest time. However, this approach has significant limitations. While it is conceptually correct, it's highly inefficient for large graphs, where the number of nodes could be as high as 10,000. Exploring all potential paths leads to exponential time complexity, making it computationally prohibitive. Additionally, the space requirements are high, either due to the recursion stack in DFS or the queue storage in BFS, making this approach impractical for real-world scenarios with large graphs. A more efficient solution is the optimized approach, which involves modifying Dijkstra's algorithm. Instead of simply tracking the shortest time to each node, we extend the algorithm to also track the second shortest time. To achieve this, we maintain two arrays for every node, one to store the shortest time, and the other to store the second shortest time. The algorithm uses a priority queue to process nodes in increasing order of travel time, ensuring the greedy nature of Dijkstra's method is preserved. For each neighbor of the current node, we check if the path provides a better time than what is already recorded in the arrays. If it does, we update the shortest or second shortest time accordingly. There are some important observations to note here. First, the second shortest path must differ from the shortest path at least by one edge, which ensures the paths are distinct. Second, the prioritized processing of nodes guarantees we only compute valid times. By tracking 2 times per node, we eliminate the need to revisit nodes unnecessarily. This approach is computationally efficient with a time complexity of O, E * log, V, where E is the number of edges and V is the number of nodes. The space complexity is also manageable, requiring storage for the 2 arrays and the priority queue. An alternative strategy like bidirectional search might also come to mind, where we perform simultaneous searches from both the source and destination. While this can reduce the search space in some problems, it introduces additional complexity here. Specifically, the need to track 2 times per node and synchronize the searches makes this approach less suitable for our case. Given the problem's requirements, we have chosen the modified Dijkstra approach as the best strategy. This method strikes an excellent balance between efficiency and simplicity, directly addressing the need to find both the shortest and second shortest times. By leveraging the greedy nature of Dijkstra's algorithm and extending it to track 2 times per node, we avoid the inefficiencies of brute force methods while ensuring correctness. When we compare the available strategies, brute force, while simple in concept, is entirely impractical for large graphs due to its exponential time complexity. Bidirectional search, although it may reduce the search space, adds unnecessary complexity without offering significant advantages for this specific problem. In contrast, the modified Dijkstra approach is both efficient and scalable. It is well suited for large graphs, ensuring that the solution is both computationally feasible and easy to implement. Ultimately, this method is optimal for the problem, effectively balancing efficiency and correctness while adhering to the constraints of finding the second shortest time. In this problem, we are tasked with finding the second shortest time to travel from node 1, the starting point, to node n, the destination, in a weighted, directed graph. While it may sound similar to Dijkstra's shortest path algorithm, the added challenge lies in finding not the shortest, but the second shortest path, and accounting for periodic delays caused by traffic signals. To begin solving this, we first parse the input and set up the necessary data structures. The graph is represented as an adjacency list, where each edge between nodes U and V with a given travel time is stored bidirectionally in the list. This ensures we can traverse the graph efficiently in both directions. Next, we use a priority queue, or min-heap, to process nodes in the order of their travel times. This is crucial for ensuring that we explore paths in the correct sequence. Additionally, we maintain a dictionary called arrival_times, which keeps track of the 2 smallest travel times to reach each node. Finally, we initialize the heap with the starting point, node 1, at time 0, so we can begin exploring paths from there. Now, we implement a modified version of Dijkstra's algorithm to find the 2 smallest travel times to each node. While the heap is not empty, we repeatedly pop the smallest element, which gives us the current node and the time it was reached. At each step, we check whether the arrival_times for this node already contain 2 travel times. If it does, we skip further processing for this node to avoid redundant calculations. Otherwise, we add the current time to the list of arrival times for this node. Next, we explore all the neighbors of the current node. For each neighbor, we calculate the next potential arrival time by adding the edge weight to the current time. However, we also account for periodic delays caused by the change parameter. If the calculated time falls during a red signal interval, we adjust it to the next green signal interval. This adjustment ensures that we accurately simulate real-world traffic constraints. Once the adjusted time is calculated, we push the neighbor and its arrival time into the priority queue for further exploration. After processing all nodes, we check the arrival_times for the destination node, n. If it contains 2 valid travel times, we return the second smallest time as the result. Otherwise, if no second path exists, we return -1. To solve this problem effectively, several key insights must be understood. First, unlike the standard Dijkstra's algorithm, we don't stop after finding the shortest path to a node. Instead, we continue processing each node until its 2 smallest arrival times are determined, ensuring the second shortest path is considered.
Second, handling delays caused by the change parameter adds complexity.
By adjusting times to account for red signals, we simulate real-world scenarios where traffic lights affect travel.
This adjustment is crucial for the algorithm's correctness.
Third, early pruning plays a significant role in efficiency. Once a node has 2 recorded arrival times, we skip further exploration of that node, reducing unnecessary computations. The algorithm relies on 3 main data structures: an adjacency list, which officially represents the graph using space, a priority queue, or min-heap, which ensures nodes are processed in increasing order of time, with push and pop operations taking log n time, and a dictionary for arrival times, which tracks the 2 smallest times for each node. In terms of complexity, the time complexity is n plus e asterisk log n, where n is the number of nodes and e is the number of edges, as each edge is processed at most twice per node. The space complexity is n plus e, due to the adjacency list in dictionary, while the heap size is proportional to the number of nodes, n.
To solve the problem, we start by importing the necessary libraries.
The heap module will help us efficiently manage our priority queue, while defaultdict allows us to construct the graph as an adjacency list. First, we define our solution class and the second minimum method. Within the method, we begin by building the graph using the input edges. Each node is mapped to its neighbors, ensuring we can traverse the graph later. Next, we initialize a 2D list called arrival_times where each node tracks both the shortest and second shortest times to reach it. Initially, all times are set to infinity, except for the starting node, where the shortest time is 0. We then use a priority queue to simulate a modified breadth-first search or BFS. The queue starts with a tuple containing the current time, 0, and node, 1.
As we process each node, we iterate through its neighbors.
At this point, we calculate the next available time to visit a neighbor, considering the traffic signal's red or green status. If the current time falls during a red signal, we calculate the waiting period required for the signal to turn green before proceeding. Now, we update the arrival times for the neighbor node based on the calculated next_time. If this next_time is shorter than the current shortest time to the neighbor, we shift the current shortest time to the second shortest position and update the shortest time with next_time. After this update, the new shortest time is also pushed onto the priority queue for further exploration. Alternatively, if next_time is not shorter than the shortest time but is shorter than the second shortest time, we simply update the second shortest time and add it to the queue. Finally, once all nodes are processed, we return the second shortest time to reach the destination node, n. This ensures that the solution adheres to the problem's requirement of finding the second minimum time. The algorithm effectively balances the constraints of red and green signals while systematically exploring all possible paths using the priority queue. Here, we begin by building the graph using an adjacency list representation. This allows us to efficiently store and traverse the connections between nodes. We start by initializing the graph as a hash map where each node points to a list of its neighbors. Then, we iterate through the edges array to populate this graph structure, ensuring that each edge is bidirectional. Next, we set up a 2D array called arrival times to track the shortest and the second shortest times to reach each node. This array is initialized with integer.max_value to indicate that no paths have been found yet. For the starting node, node 1, the shortest arrival time is set to 0 since we start there. Finally, we set up a priority queue to implement a modified BFS. The priority queue ensures that we process nodes based on their earliest arrival times. We begin by adding the starting node, represented as 0, 1, where 0 is the current time and 1 is the node. From here, the BFS loop begins, where we process each node in order of their arrival times. Within the BFS loop, we extract the current node and its corresponding time from the priority queue. Then, for each neighboring node, we calculate the next possible time to visit it. This involves accounting for red and green signal cycles. If the current time falls within a red signal, we compute the waiting time required to reach the next green signal. The total travel time to the neighbor is then calculated as the current time plus the waiting period and the travel time between nodes. Once we determine the next time, we update the arrival times array. If this time is shorter than the current shortest time for the neighbor, we update both the shortest and the second shortest times accordingly and add this path to the priority queue. If the time is not the shortest but is shorter than the second shortest, we update only the second shortest time and add this path to the queue as well. After processing all neighbors, the BFS continues until the priority queue is empty. At the end, the second minimum time to reach the destination node n is stored in arrival times, n1, which we return as the result of the function. To solve this problem, we start by constructing the graph as an adjacency list based on the given edges. Here, the graph is represented as 1, 2, 3, 2, 1, 3, 1, 4, 4, 3, which means node 1 connects to nodes 2 and 3, node 2 connects back to node 1, and so on. Next, we initialize an arrival_times array, where arrival_times I0 stores the shortest time to reach node I, and arrival_times I1 stores the second shortest time. At the beginning, all values are set to infinity except for the starting node, which is initialized as 0, INF, for node 1. We also initialize a priority queue with the starting node in time 0, 1. Now, we begin the BFS iteration. In the first iteration, we pop 0, 1 from the queue, meaning we are at node 1 at time 0. From here, we explore neighbors, node 2 and node 3, each of which can be reached in 2 units of time. This updates their respective arrival_times to 2, INF, for both nodes, and we push these states, 2, 2, and 2, 3, into the queue for further exploration. As the BFS continues, we process the next node in the queue, which is 2, 2, at node 2 with a time of 2. From here, we explore its neighbors, but the only neighbor is node 1, which has already been visited with a shorter time, so no updates are made. Next, we process 2, 3, meaning we're at node 3 at time 2. From node 3, we explore its neighbors, which include node 1 and node 4. Node 1 has already been visited, so we skip it. For node 4, the calculated next underscore time is 4, so we update its arrival_times to 4, INF, and push 4, 4 into the queue. Finally, we process 4, 4 at node 4 with a time of 4. From here, we explore its only neighbor, node 3, which has already been visited, so no updates are made. At the end of the BFS, we check the arrival_times for node 4. The second minimum time remains infinity, which indicates that no second path exists to reach the destination. Now, let's analyze a slightly more complex example with signal weights. The graph here is constructed as 1, 2, 3, 2, 1, 5, 3, 1, 4, 4, 3, 5, 5, 4, 2, reflecting the edges provided. The arrival_times array is set up similarly as before, with all values initialized to infinity except for the starting node, which is 0, INF, for node 1. The priority queue is initialized with 0, 1. In the first BFS iteration, we process 0, 1. From node 1, we explore neighbors 2 and 3, both of which can be reached in 3 units of time. Their arrival_times are updated to 3, INF, and we push 3, 2, and 3, 3 into the queue for further exploration. Signal weights don't affect this iteration yet because the travel time of 3 doesn't cross any signal boundaries. Next, we process 3, 2 from the queue. From node 2, we explore its neighbors, node 1, which is already visited, and node 5. To reach node 5, the travel time would be 6, but since the signal cycle has a red phase at this time, 5 to 10, we must wait until the light turns green, making the next underscore time 11. We update node 5's arrival_times to 11, INF, and push 11, 5 into the queue. We then continue exploring paths from node 3 and node 5, ensuring that signal weights are accounted for by checking whether the current time falls within a red phase. Finally, after processing all nodes, the algorithm determines that the second minimum time to reach node 5 is 14. This example highlights the importance of adjusting travel times based on signal weights. The algorithm guarantees correctness by only updating paths when shorter times are found, and the priority queue ensures that the smallest time is processed first, maintaining the optimality of both the shortest and the second shortest paths. Here, we begin by analyzing the time complexity of the solution. The first step is the graph construction, where we build an adjacency list. This requires iterating through all the edges in the graph, which gives us a complexity of O(e), where e is the number of edges. Next, we consider the modified BFS algorithm. In this approach, the priority queue is central to the traversal process. Each node can be processed up to twice since we are tracking both the shortest and second shortest paths.
This means that in the worst case, every edge will be relaxed twice, leading to 2 operations.
For each operation in the priority queue, the insertion or removal of nodes takes O log v, where v is the number of nodes.
Combining these, the graph traversal, which processes all nodes and edges, results in an overall complexity of O v plus e asterisk log v. Now, we consider the signal waiting time. For each step of the traversal, the signal waiting time is calculated. Since this involves basic arithmetic, it has a constant time complexity of O1. When applied across all nodes and edges, its contribution becomes O v plus e. Combining the complexities of graph construction, modified BFS, and signal waiting time, the overall time complexity of the solution is O v plus e asterisk log v, where v is the number of nodes and e is the number of edges. Moving to space complexity, we start with the graph representation. Using an adjacency list, the storage requirement is O v plus e, because we store every node and its edges. Additionally, we maintain a 2D list to track the shortest and second shortest arrival times for each node, which contributes O v to the space complexity. The priority queue also contributes to the space complexity. In the worst case, it may hold up to 2 v elements since each node could be processed twice. This results in an additional O v space requirement. When combined with the space needed for the graph representation and arrival times, the overall space complexity of the algorithm becomes O v plus e. To put this in perspective, let's compare it to a brute force approach. In a naive solution, we would enumerate all possible paths from the starting node to the destination node, calculating the travel time for each path to identify the second minimum time. This approach would require exploring all paths in the graph, leading to an exponential time complexity of O2 to the power of v, in the worst case, which becomes computationally infeasible for larger graphs. The optimized approach, on the other hand, leverages a modified BFS with a priority queue. This allows us to efficiently compute the shortest and second shortest times while significantly reducing the complexity. Instead of exponential growth, the optimized solution runs in O v plus e asterisk log v, making it suitable even for dense graphs with up to 10 to the power of 4 nodes and edges. Analyzing the best, average, and worst cases, we see that the algorithm performs well across different scenarios. In the best case, where the graph is sparse and the shortest path is easily found, the algorithm processes fewer nodes and edges, achieving near linear performance of O v plus e. For a moderately connected graph, the average case is around O v plus e asterisk log v, as most nodes and edges are processed. Finally, even in the worst case of a dense graph with full connectivity, the algorithm remains efficient due to its reliance on priority queue operations, maintaining the same O v plus e asterisk log v complexity. In conclusion, the optimized solution demonstrates significant improvements over a brute force approach. By using BFS in combination with a priority queue, the algorithm efficiently computes the second minimum time to reach the destination. Its time complexity of O v plus e asterisk log v and space complexity of O v plus e make it highly scalable and well suited for handling large graphs. This balance of efficiency in both time and space ensures that the solution is practical for real-world applications involving graphs with a substantial number of nodes and edges. When working on this problem, there are several common mistakes to watch out for. First, a major issue is not handling the second minimum time correctly. Many people assume that a straightforward BFS or Dijkstra's algorithm will automatically give them the second minimum time, but this is not true. These algorithms are designed to find the shortest path, not the second shortest. To solve this, you need to explicitly track multiple times for each node and ensure that the second smallest time is distinct from the smallest. Another frequent mistake is overlooking edge cases, such as disconnected graphs or cases where no path exists. Ignoring these situations can lead to runtime errors, infinite loops, or incorrect outputs. Additionally, using an inefficient graph representation can be a pitfall. For example, an adjacency matrix may seem convenient, but it consumes n squared space, which is impractical for large, sparse graphs. Instead, adjacency lists are a better choice for efficiency in these scenarios. Another key consideration is accounting for time constraints. A common mistake is not properly handling the waiting times at nodes.
If the departure time from a node does not align with the specified interval, your solution could be incorrect, so it's crucial to calculate departure times carefully. There's also confusion about what constitutes the second minimum path. Some assume that the second minimum must involve a completely different route, but that's not always true. The second minimum time can result from revisiting the same edges, but with different timing constraints. This highlights the importance of understanding how timing impacts the paths and ensuring that all scenarios are considered. When approaching this problem in an interview, there are a few insights to keep in mind. First, it's vital to clearly understand the problem's requirements. Focus on how the second minimum time differs from the shortest, and make sure to clarify edge cases, constraints, and expected outputs with the interviewer. Since graphs in these problems are often sparse, optimizing your solution with adjacency lists and priority queues, such as Python's Heap, is important for efficiency. You should also use a statespace approach to track both the shortest and second shortest times for each node. Be prepared to explain how you handle waiting times at nodes, as this can be a critical part of the problem. Additionally, interviewers may ask about trade-offs, so you should be ready to justify your approach in terms of time and space complexity. Finally, this problem shares similarities with related problems like network delay time and number of ways to arrive at destination, so reviewing these can help reinforce your understanding of graph traversal concepts. There are several alternative approaches you can consider for this problem. One option is a modified version of Dijkstra's algorithm. This method extends the algorithm to store the two smallest times for each node, making it efficient while avoiding redundant traversal. However, it does require extra bookkeeping to track these times. Another approach is to use BFS with states. In this method, you track 2 times per node, the shortest and the second shortest. While this can be simpler to implement than the modified Dijkstra's approach, it tends to be less efficient for graphs with large edge weights. Lastly, you might explore bidirectional search, where you perform simultaneous searches from both the source and destination. This can help reduce the search space, but it complicates the handling of time intervals and the tracking of second minimum times. Each approach has its strengths and trade-offs, so the choice depends on the specific requirements of the problem and the constraints you're working with. Great job! We've covered the problem and its solution, emphasizing key techniques and takeaways. Remember, this approach is useful in scenarios requiring secondary optimal solutions. Thanks for tuning in, and be sure to like, subscribe, and share for more problem-solving insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!